Okay. Now, so basically, these are the formulas that we would be using, but there's something that I would like to show. Okay, but let me not talk this. Let me just pick an example, then we continue from there. Um, so let's solve this together. We have h of x being equal to x minus 1 on x plus 1. So once again, I'll appreciate if a number of us can solve this along. Okay, if you can solve this along, that would be very, very, very nice. Now, the reason why I brought this question is so that we identify how to solve composite functions. Most of the differentiation questions that we get, they are basically composite questions, such as this one. So let me explain the composite function in this case. For instance, you have y is equal to cos u, right? Now, this cos u is a composite function. Why? Because u is found. So basically, we can rewrite this as g of x is equal to cos, let's say cos t, and f of x is equal to u. So g of f of x basically gives us the cos u, right? I want everyone to follow here. The way we solve this is basically the y on the u is equal to cos u times u prime. But in the case of x, please let's follow at this point. It's very important. For the case of x, we have y is equal to cos of x, and we oh sorry, this is sine rather. Oh, no one corrected me. So differential of cos is negative sine of x, right? So negative sine of x, sine of u and u prime. Okay. Now, as I was saying, in the case of differentiating with respect to x, we get something similar. The y on the x is equal to, again, we differentiate the outer function, which is what? Negative sine of x times the differential of the inner function, which in this case is x. And we know that the differential of x is 1. So we have 1. That's why the differential of cos x is just negative sine of x. There is actually a differential of x somewhere, but because it's 1, we don't bring it. Hope it's clear. Now, that's something similar that this function, a similar form is in this function also, right? And most of the questions that come, they want to test your understanding on this. So let's look at this. We have h prime of x. You can do it the h on the x bar, h prime of x makes it much easier, right? Now, view this way. This entire function that you are seeing over here is your u, and you have u to the power 3. So how do you differentiate u to the power 3? This is a composite function. So it differentiates the outer function first, which is what? 3u squared times u prime. So in this case, we differentiate the outer function, which is what? 3, and we write the original again. The original is x minus 1 on x plus 1 on 2. So what we've done basically is that we've differentiated the outer function. As in this case, we differentiated the 3u squared and we rewrote our original u without it being changed. Now, what we have to do is differentiate u again and multiply. This we have this x on 1 and x plus 1 is the quotient rule, right? And you can break down your solution and solve it. That way, when you have an error or something, it makes it easier for you to identify. So the quotient rule follows the formula u on v. U on v is equal to v squared. You write your v u prime minus v prime u. The order is very important. If you swap this, you will get a negated form of the answer, right? So you first go with the v, then you write v again, u prime, v prime, and u, right? Now, the way I like to solve a quotient using the quotient rule is that I know my u is equal to 1 minus x. So I come here and do u prime. U prime is equal to 1. I find my v. V is equal to x plus 1. And v prime is equal to, of course, v prime is 1. The reason why this method makes it is much advisable is because, believe me, you'll be getting much complex functions than we have over here. And usually it's combined with strict, right? So even if you present it in this form, if you get any wrong along the way, you are able to get something for the solution that you've provided, right? So again, let's continue with our solution. So this times the differential of the inner part, which is what? So let's solve it first over here. So v is 1, u prime, sorry, v is x plus 1, u prime is 1, all this minus v prime. V prime is 1, u is x minus 1, all on v squared. V squared is x plus 1 all squared. Most people don't get differentiation questions wrong because they don't know how to go about it. No, that's not the reason. The reason is that like some tiny plus that you change to positive somewhere here and it affects everything. That's basically why most people get the differentiation questions wrong. Okay, apart from the fact that people don't know how to really solve complex composite functions. This is not really complex, but hopefully we'll be taking more examples that are a bit more complex. Okay, so we have x plus 1 minus x plus 1, all on x plus 1, everything is squared. X cancels out and we get 2 on x plus 1, everything squared, right? So what you've done here basically is the differential of this. So we come here and multiply everything by 2 on x plus 1. So with this format, if you are going through your work, when you are done, it becomes much easier. You can leave it in this way, but depending on the question, if the question says simplify, then of course you have to simplify, right? So we have 2 times 3 giving us 6 x minus 1 all squared, everything on x plus 1. This is to the power 2 plus 1, so x plus 1 to the power 3. Okay. Let's take one more example. Um, let's see. I'd like to take an example on a different topic. So let's pick one on trig. So let's go to the topic derivatives of trigonometric functions. So let's pick one more example of a similar format. We have y is equal to cos, let's do cot t squared sine theta. One thing you have to take note of is the theta over here. It's very important. The factor that you are differentiating by is very important, okay? And we'll be seeing that in at the latter part of the class why it's important. Okay. So again, this is a composite function, right? But let's first of all make this clearer. This can be written as y is equal to cot sine theta, everything squared. So the y on the theta, not the x, the theta, is equal to, again, let our cot sine theta be u. So we have basically u squared. So the differential of this gives us 2u to the power 1 times u prime, right? So we have 2, our u is cot so cot sine theta times u prime. Now u prime is the differential of this entire expression. So now we have another expression to differentiate. We have cot sine theta to differentiate. Now again, it follows a similar trend where sine theta now becomes our u. So what's the differential of cos theta? Cos theta is, let's refer, cos theta is negative cosec squared theta, right? Please, we will be solving the next example. Negative cosec squared theta. Okay, and again, we write our u unchanged. Then we differentiate our u. Just so cot u, the differential of this is negative cosec u times the differential of u. Now the differential, now u is sine theta, so differential of u gives us cos theta. This is what we have. So what we've done here basically is our differential of this inner function. I'm using the term function because we are dealing with composite functions over here, right? So we get cot 2 theta. We are getting this because we differentiated the outer function, which is, we brought the 2 forward. This is now to the power 1. And of course, our inner function remains unchanged. We differentiated this over here, and we have negative cosec square theta. Oh, so this was a terrible error I made, and a very, very terrible error. You shouldn't have the theta over here, okay? Because your theta is now your sine theta. I hope you get what I'm saying, right? This is not like cos 2x. Let me not use what. This is not 2x times sine x. If this was basically what we were solving, we would have used the product rule. But as you can see, the product rule does not hold in this case because you don't have to. Cosec square is not multiplying sine theta. Sine theta is rather the x or the value you put into the cosec square theta, right? So let's clean this and let's continue from there. Times sine theta and all this times cos theta. So from here, you have to simplify this expression that you have carefully, right? Or you can leave it this way if you can. If you can't simplify, please leave it in the way that you find it best. Okay, but let's see if you can simplify this. So we have cos theta, you have sin theta. So basically, this becomes our final answer. All you have to do is to take your negative over here, then you are done, right? You don't have to bring this multiplication sign. This becomes our final answer. Okay, so let's take one example. Let's take one example and solve together. Let's solve this example together. I'll be taking the answers in the comment section. So we solve this in 5 minutes. So y is equal to x squared sine squared 2x squared. So this is the question we are all trying. Let's write the question down and try to answer it. So at 4:26, I'll be taking my answers in the comment section. I don't have access to my WhatsApp, so please, if you send me a message lately and I've not replied, I'm very sorry. I'll reply as soon as I get my WhatsApp. Yeah. What's this? Okay. Okay. So let me see any. Okay, not yet. Okay, so let's see if we have any solutions. So let's solve this. Um, how would you write? How would we be able to write x squared here? Okay, sure, makes a lot of sense. But you can also send a picture of it if you are okay. But if not, that's fine. Okay. I realize the answer is very long. It's very long. Yeah, it's fine. So let's solve this together. Thank you very much for the attempt. Okay. Just a minute. So let's solve this systematically. Okay. Um, so how many functions do we, separate functions do we have? We have two separate functions. We have x squared and we have this one as well, right? So we can basically use the product to, we say that let y be equal to u v. So the differential of y is equal to u prime v plus u v prime. Is basically what we get. Okay. So our u is x squared and our v is sine squared 2x squared. So u prime is equal to 2x and v prime is equal to, let's see what u prime is equal to. V is, let's see what v prime is equal to, sorry. V is sine squared 2x squared. This is what we have for v. So the differential of v is a composite, so we can write, let's rewrite v as well, right? We have sine 2x squared closed squared. So v prime is 2 sine 2x squared times the differential of the inner function that we have. So the differential of sine 2x squared is cos, again we write the inner function 2x squared times the differential again of the inner function. So once you have inner functions, like you have a function inside that you've not touched, you differentiate its outer one. If there's one inside, you differentiate again and it goes in that order, right? Times, let's see, what do we have? Times 4x, right? So this is what we get for v. Let's see if you can simplify it. This is what we get for v prime, sorry. We get 2, let's bring all the constants to one side. We have 8x sine of 2x squared times cos 2x squared. So this is what we get for v prime as well. So this gives us 8x sine of 2x squared times cos 2x squared. Now all we have to do is to make the substitution. So y prime is u prime 2x times v is sine squared 2x squared plus u is x squared and v prime is let's make this one 3 because x squared times x gives us x to the power 3, and we are left with sine of 2x squared cos 2x squared. So this becomes our final answer. So we can see once we break this down into simpler functions, it becomes much easier for us to solve. If we were just to jump into this function, solving the product along with the composite side of the function as together, we would probably get something more messy. right? So as much as possible, try and break your function down, right? Now, let's take a question on implicit differentiation. So implicit differentiation basically is differentiating with respect to x, y, or any other variable that you are given. Okay, that's what implicit differentiation is about. So let's say we have a function that goes this way: 4 squared minus 2y to the power 3 plus x cubed y squared minus cos x is equal to 8. This is the function that we have. So the differential with respect to y, right? So usually, usually when you have a function like y is equal to 2x, when you are differentiating this, you say dy dx is equal to 2x. What you've actually done in this case is you are saying, okay, I'm differentiating with respect to y, right? So wherever I see y, I bring the y on the x. How should I explain this? Um, um, yes, and the differential of this constant y is 1, and we have 2 2 times 1 basically, right? That's why we get the y dx is equal to 2. So what I'm trying to explain is that even when you differentiate and you get the y dx, you are actually differentiating the y again, and you're multiplying by the answer that you get, which is 1. In this case also, with respect to implicit differentiation, when you differentiate y to the power 4, you basically get 4y to the power 3. And again, you bring your dy dx. So times dy on the x. So again, this gives us 6. Because this is a constant, you can throw your constants away somewhere, differentiate your variable, and attach it back. So the differential of y to the power 3 gives us 3y squared times our constant, which is 6. So 6y squared times dy dx. Let me cast this part. Right, 6y squared times dy on dx. This is a product rule, right? So let's solve this separately somewhere. X cubed y squared. This gives us x 3x squared y squared plus 2y. We are differentiating y, so we bring our dy dx, and of course x cubed. What we've basically done is using the form, the product rule uv, where this is our u prime, this our v, this becomes our v prime, and this becomes our u. We've done the product rule over here. Right, so let's bring this back into our question that we have. So we have plus x cubed y squared, whose differential is now this. Right, so we have plus 3x squared y squared plus 2y dy on dx, x to the power 3. Right, the differential of course is negative sign, so the negative becomes positive. We have sine x, and of course differential of a constant is 0. So all we have to, once you get this first step, you are basically done, right? So the second step is now to group like terms. So we group every term with the dy dx, which is 1, 2, and 3. So we basically have 4y cubed dy on dx minus 6y squared dy on dx plus 2y x cubed dy on dx, and this is equal to negative sine x is negative sine x minus 3x squared y squared. Right, so dy dx is, you factor out dy dx, you get 4y cubed minus 6y squared plus 2y x cubed, and this is equal to sine x minus 3x squared y squared. And this becomes your final answer. If you can simplify, simplify. If there, okay, no, you can't simplify. So this becomes your final answer. Right. Now, for the question for, there was a past question, I think about 2 years ago. And the format of the question was that show that the second differential is equal to a particular answer, right? And let's see, when you solved this, this was how the answer was. So when you find, it was even the second derivative, right? The question was find the second derivative, the y on the x. And the answer they basically got was somehow in this format. So imagine you solve the second derivative and you get x squared sine, let's see, what is the question? So if you get this for a final answer, x squared sine 2x squared, all on this answer that we had, 4y squared minus 6y squared plus 2yx cubed. Now, they said I showed that the question said, show that the second derivative, the square y on the x something, I don't, of course, I'm already listed, is equal to y on, no, it wasn't equal to y. It's equal to, yes, it's equal to 8 4y squared minus 6y squared plus 2yx squared. Now, this is a very important part. One of the best question you can get on differentiation or integration is a show question. Because when you solve it, you know that your answer is right. When it's wrong, you clearly know that your answer is wrong, so try again. Right? So the question that came in, I think 2 years, or it has come 2 times, right? Something very similar to this. And there's an example also in the exercises. I think the slides as well. They brought the same question. Show that the second differential is equal to something like this. Now, most people solved the second differential, they got the answer, right? But they didn't get the show that was asked of them. Now, the question was in this format. Once you solve the second differential, you get your answer. But it's up to you to know that this numerator, right? This numerator is actually your y. It's actually your y, exactly. So, no, we're doing implicit differentiation. Oh, I wanted to make an example. So what I was trying to do is that, let's see, this was implicit and this is equal to 8, right? So we get this y is equal to, like, so this will not be there. So you basically get this as your numerator, and they will give you the 8 as show. The 8 will probably go to 0 because of differentiation, and it's up to you to know that this expression over here from the original question is equal to 8. This trend is very, very, very common, right? It's very, very, very common, and they carry a lot of marks because of the long process involved. So let's take note of such a question. So we've taken a question on logarithmic differentiation. We've just done one on implicit differentiation. We've done one also on trigonometric differentiation, and we are making progress, right? So let's pick one more example. But before then, are there any questions? Let me check my message. Hello. Are there any questions, please? Any questions? Any questions? Any concern or any part that you would like us to go over one more time? Okay. So what's the next one? So let's look at the differentiation of exponential function. The differentiation of exponential function. So let's use this question. Let's okay. Let me combine exponential with trig. So let's have y is equal to e to the x, and we have cos x. This is the question that we have. Now let's go over something. Okay. So the differential of, so let's y be equal to e to the u. The differential, the y on the u, or basically u prime, is equal to eu times u prime. So if you have y to be equal to e to the power 5x squared, u y prime will be equal to the differential of 5x squared. The differential will be equal to 5x squared. The differential will be 10x times e to the 5x squared. Right. So basically in this question, our answer is y prime is equal to our original question, e cos x times the differential of our top. Now at the top we have a product rule, right? The differential of x is 1 times cos x, right? This times 1 plus we have our original one, which is the x, right? Because it's basically u v prime plus u prime v. Okay, so we differentiate one, multiply by the other one, unchanged, differentiate the other, and multiplied by the other one, also unchanged. So we have x multiplied by the differential of the other, which is negative sine of x. So this becomes negative sine x. So we have u prime to be equal to ex cos x minus x sine x. And this becomes our final answer. Right, so let's take one more example, which let's see if I can get a tougher example for us to solve. Anyway, if you want to practice any form of differentiation or integration, right? I've sent a book to the group. It's called Dr. Ben recommended something. Okay. And that book is very good. It has 1,001 practice questions, and each question has a solution. Some of them even have explanations attached to them. If you still don't have it, kindly DM me after the class and I'll send them to you. Okay. So let's take a different form of exponential derivative of exponential functions, not necessarily e, right? So we are doing so much today, as I promised, so much today, and I hope you've watched the videos as we agreed on. So when let's forget about this for in the first place, we've seen the differential of e to the u, which we said is e to the u times u prime. And there's one more we have to note which is what natural log of u, which is u prime on u. So in the case of the natural log, the natural log doesn't appear anymore, right? But in the case of the e to the u, the original one also appears again. Now this is a special case, I should say. This is a special case. You can't just differentiate this, right? But there are formulas for this, but I don't advise using formulas for differentiation because it's not quite safe. Okay. So how we can do this is that we can take the natural log of both sides. We get natural log of y is equal to natural log of 10 1 minus x squared. So this becomes natural log of y is equal to, we can bring this down, right? So 1 minus x squared. Remember, everything is being multiplied by 10x. So in this case, we have the product rule. So the differential of this gives us dy dx. Remember the formula for the differential of the natural log of u, right? So the differential of y gives us 1 and the original y. And this is equal to 1 minus x squared natural log of 10. So the y on the x is equal to 1 minus x squared natural log of 10 times y. Our y is our original question. So this finally becomes dy on the x is equal to 10 and what, sorry, 1 minus x squared natural log of 10, and our original question 10 1 minus x squared. So this becomes our final answer. Okay, so let me start this up a bit. The page is looking too dry. So when you have a question in this form, all you have to do is to bring down your exponent, right? So but you can do that by taking natural log of both sides. You get something in this format. Of course, usually you get a product rule. Then you apply the product rule from there. As I said, there's a formula for this, but using the formula in calculation is not the best, right? So let's take a question on let's still stay on logarithmic, or what am I saying? Logarithmic functions, derivatives of logarithmic functions. But this one, let's take one that has the natural log, right? So f of x is equal to x squared natural log of 1 minus x squared. I really appreciate if we can solve along, right? I really appreciate if you can solve along. This would be the best. Okay, so by the time you finish, you've probably practiced about 20 questions. If you're able to solve along, then you've actually seen how how you've done so far, right? Because we are solving along. So if there's any part you make a mistake, then you can easily refer, right? So let's solve this question. We have f of x, and again, this is the product rule. So f prime of x is equal to x squared, the differential of this, which is negative 2x on 1 minus x squared plus 2x and the original question 1 minus x squared. So what we have to do is simplify this question, this expression. We have negative 2x cubed all on 1 minus x squared plus 2x natural log of 1 minus x squared. And this becomes our final answer. Okay. So let's take one that involves actual log. So let's have f of x. No, first of all, let me ask this question. Please, okay, can I go over implicit differentiation? Okay, I'll go over it before I continue. Any more questions, please? Thank you very much, Kojo. I really appreciate this. Any more questions? Any other thing that anyone wants me to go over? Any other thing? Okay. Please, if you have any concern, can you please mute unmute and speak? Okay. That would be very, very, very nice. So let me write the question down. But let me go over the implicit differentiation first. Let's see, implicit differentiation. Sure. So let's take this question. Xy, the square root of xy is equal to x squared plus 2y squared. Now, for the implicit differentiation, right? For the implicit differentiation, you will have more than one y. Usually, in most questions, you have just one y. So differentiating the y will give us the y on the x. So basically, wherever you differentiate y, you bring the y dx. This is the first one, right? This is the first one. Now, we are differentiating with respect to x. So if there was, let's say, plus z, a differential of z would have been the z on the x. This is what it looks like. So let's actually see what this part is. This expression looks like. I've added a z to it, but I'll take it off later. This is actually 2x dx on dx plus 4y, because 2 is multiplying 2, we get 4y dy on dx plus dz on dx, of course, times 1, right? But the 1 becomes almost negligible. You have to understand this. Once you understand this, everything becomes much more clear. So simplifying this, because we have the x on the x, it cancels out, and we basically get 2x plus 4y dy on the x plus dz on the x, because you are differentiating with respect to x. Let's go over this again. This is the question that we have. Now, with implicit differentiation, depending on, so what I mean by with respect to, right, it means that you are differentiating with x, like by x. Do you get it? So the derivative of x squared is the x on the x. The derivative of y is the y on the x. The derivative of z is the z on the x. But by what you are differentiating by, since you are differentiating by it, it basically cancels out. So it looks like we are basically ignoring the something, right? The x on the x or the y on the x. But no, we don't bring it because it's basically canceling out. So let's solve this question again. We have the square root of xy is equal to x squared plus 2y squared. This is the original question that we have. Okay. So what I like to do is to rewrite this question in a form that makes it very easier for me to see. So the derivative of this gives us 1 on 2. Again, this is a composite, so xy to the power negative 1 on 2 times the derivative of the inner function. So this gives us the derivative of x, which is 1 times y. Of course, the product, we are using the product rule here. So this plus the original x here times the derivative of y, which was dy on the x. Right. So this is equal to 2x. You don't bring the x on the x because you are differentiating with respect to x, and that thing cancels out, right? So plus 4y dy on the x. right? So we
wait, this hold on. I'm a bit
okay,
confused with the how you open the square root part. Can't you just use the product rule to do this, or it's not going?
okay. So with this part, right, with this the left hand side. Okay. So using a product rule, let's see. Okay. So let's try using a product rule. So using a product rule to solve root of x, y, you can actually use a product rule. Okay. So let's try it and see.
Yeah,
We get
yeah.
x to
So
the
like,
power.
let's say, like, so for the x, you get something like, let's say, um, how differentiating the x, you get one, right? So like how y to the power, then plus for the y to how x to the power. I don't know if that makes sense.
Yeah,
Yeah,
it makes so much
exactly.
sense. It makes a lot of sense.
But no,
Hmm.
you finish with yours and let me just compare whether
Oh,
it's the
let's
same as
let's
mine.
let's okay, sure. That's amazing. But this might okay. So you can use both of them, okay, but maybe just maybe it might be longer, right? It might be longer, but you can use both. Both will be equally correct, right? So this gives us 1 on 2 the square root of xy times what am I seeing? Y plus x dy on dx. 2x plus 4y dy on dx. Right. So we basically multiply each. Please, is this the same thing you had for your differentiation, or you had something a bit different?
No, it's the same.
Oh, okay. Thank you very much.
You just
So
factored. Yes, it's the same.
okay, that's amazing. So we get y on 2 root of xy plus x dy on the x on 2xy, and this is equal to 2x plus 4y dy on the x. And this where things get really some way. It's not that you don't know, you've actually gotten this step, but this step is actually also very important, right? The way you go about this step is very important. So um how can we go about this? Let's try and get rid of our denominator, but of course multiplying both sides by 2 root of xy, right? So we get y plus x dy on the x. 2x times 2 root of xy gives us 4 root of xy x, which will be later simplify, which will simplify very soon, plus 4, sorry, this gives us 8 y dy on the x gain root of xy. So let's take our dy dx to one side, and we get x dy on the x minus 8y dy on the x. And this is equal to, we've left one out, xy. This is equal to our y, negative y, of course, our 4 So we basically have x to the power half plus 1, which is x to the power 3 on 2. So let's basically write it like that. X to the power 3 on 2 y. So let's cross check. We have this. So we should have simplified this part also. Let's do so before we proceed. That's my eraser. Three on 2 half. Okay. So the y on the x is giving us x minus 8 root of x y cube. Wow, is this correct? Y cube. Yes, it's correct. And it's equal to negative y 4 root of x cube y. Right. So we divide this also by x minus 8 root of x. So you can basically bring this together, right? So root of, and this becomes your final answer. Something similar. No, this can't hold. And so this basically becomes your final answer. You can't factor out anything and divide. So you are basically left to do this. Right? And it looks some way, but um yes. So let me see if there are questions in the chat. Any questions in the chat? So I've gone over implicit differentiation. Okay. So let's continue with this kind of differentiation. Okay. Let's take one question that actually involves a log. Okay, so we have f of x being equal to log to the base 10 of 2 plus sine x. Now the derivative of, let's see, the derivative of log to the base a of u. Let me say it in this format rather. Is, let's say y is equal to this, y prime is u prime on u, and the denominator times the natural log of your base. So the base here. So the base is a. So this becomes the formula for the differential for of natural logarithms, right? Remember that natural log is also a similar case, right? Let me check something on the calculator real quick. Natural log of 10. Or I don't know why, but there's actually a strong relation between y is equals natural log of x and this one, right? You can actually write this one in this form. And you see that it makes so much sense why this. So basically, the natural log differentiation formula, right, which is u prime on u, got its formula from the original log something. But just that with the natural log, it has the base of e, exactly. So we also have natural log of the base, and in the case of the natural logs, we have a base of e. So this basically becomes 1, and you get your original u prime on u back. So that's basically the proof. Is it a proof? I should say. No, that's not a proof. Right. So the differential of the log is basically u prime on u times the natural log to the base of to the natural log of the base. Yes. Right. Something like this. I have to check it to find the entire proof. But yeah, this something very similar to it. Okay, so let's proceed. So again, f prime of f of x is equal to, you can't just start and say dy dx. No, this is totally wrong. If you want to use y when you've been given f of x, you have to say let y be equal to this before you start, right? Again, if the original function you were given where x is greater than 2, once you write this original question again, you have to bring the interval, not just for calculus, but for every maths question that is defined on a certain interval. Okay. You are having a recap of what you've done over the last classes. So dy on the x is, so we have u prime. What the differential of the inner part is basically cos of x, because the 2 goes away and we have cos x. And this is on 2 plus sine x, our original u, times the natural log of our base, the natural log of 10. And this becomes our final answer. So all the types of differentiation that we've gone through, like um every single one of them follows the same format, right? But the part that becomes tricky or confusing is when different types are combined. So you can have a question like log to the base, this same question, but with the 2, you'll not be having 2, you'll have something like sine square tan 5x plus, let's see, e to the x sine x. So you'll be getting something similar to this, right? And how do you go about it? Once you break them down into pieces, this looks simple, right? This looks simple. Even if this doesn't look simple, we know it is the product rule. We know how to solve the differential of tan. Like once you start to break it down, no matter the question that you are given, you see that everything becomes much, much, much easier, right? Everything becomes much easier. So let me see something. So let's take, are there any questions? We are moving a bit higher, but before then, I would like to take a question. Any questions, please? Any questions? Any questions? Okay, so let's proceed. So let's look at the differential of parametric um, derivative of a function in parametric form. All right, derivative of a function in parametric form. Now, I'll not be going over the concept of something because it's not because it's basically not important. It won't be examined on. But basically, let's say we have two functions. X is equal to f of t and y is equal to g of t. These are the two functions that we have. Now, you are being asked to find the y on the x. Please, you can't divide these two and do something like y on x and f on t and conjure your answer. No, please, it doesn't work that way. Okay, so the way you can go about solving this question is you can find, so let me use an example, right? So let x be equal to t minus t squared and y be equal to t minus t cubed. So we are differentiating with respect to t. So we won't get the t on the x, no. We rather get the x on the t. Please, do we get it? We are used to the form that the x is always at the bottom, but no, in this case, x is not at the bottom because how should I explain this? Because it's not at the bottom. We are differentiating with respect to t. Okay. I hope that makes sense. By the way, make I'm confusing myself. So the x on the t is equal to 1 So the t is going to take every property that x takes. So when you differentiate x, you basically get 1. You don't get the t on the whatever. Minus 2t, right? Derivative of y is dy on the t, and this is equal to 1 minus 3t squared. Now, this way it gets important. Dy on the x is equal to dy on the t times dt on the x. So by observing, right, you can basically cancel this out and you get the y on the x. But please don't cancel out anything. Like once you cancel out, yeah, it's basically wrong. It's not, there are no values that we cancel out, right? So once you write this, you are good to go. Okay. Now this is the t d dy dt. This is our dy dt. And from here we can see something similar to dt dx, but it has been changed. So all we have to do is to reciprocate our function again. Let's go over this again. We have x is equal to t to the power, what am I saying? We have x is equal to t minus t squared and y is t minus t cubed. We found the x dt with respect to t, right? So as I was saying, t takes every property of x. So the derivative of t gave us 1, the derivative of t squared gave us negative t. Similarly, we do the same thing for the other side of the equation. Now we have the two equations. Remember that it's respect to t, so t is in the denominator, and we are looking for dy on the x. So we can rewrite this dy dx in terms of dy dt and the t dx, such that we get two different derivatives that can give us what we've been asked to look for, right? So dy on the x is equal to dy dt, which is 1 minus 3t squared, times what? The t dx. The t dx is the reciprocal of the x dt. So we get 1 on 1 minus 2t. So this becomes 1 minus 3t squared minus 1 minus 2t. And this becomes our final answer. Right, this becomes our final answer. So we are left with some forms of differentiation, higher derivatives, which is like you are finding the square, you are differentiating 2 times, 3 times, and in that order. We are also left with differentiation, derivatives of inverse trigonometric functions. And I think that's all. Is that all? Yes, so these are the two topics that we are left with. These are the two topics that we are left with. Okay. Okay. So let's take, I want us to take one more of them. Okay. So I plan to do this later, but hey, I think I should just do it. Or let me just brush on it. This will be the final thing that we would be doing for today. Let's see. So let's take note of these formulas. Derivatives of inverse trig functions, right? Derivatives of inverse trig functions. Let me see if I can get it in the slides. Okay. I think the proof. Let me see the proof before. So they've actually separated them. Yeah, so you can also learn the proof of this. It's not hard. So let's go over one proof. Which one will be easier? Let me take the sine. I think the sine will be easier. Let's see. So the derivative of, let me find the, let me take the example from the internet. Derivatives of inverse rate. I'll be sending a formula sheet that we can use in the differentiation. I think there's one and it's very good. So I'll search for it and see if I can get it. When I do, I'll send to the group. Okay, so let's try and prove the first one. It's a question I've seen before. So let's prove the first one. So sine inverse of x. Let sine inverse of x be equal to y. So we have sine of y is equal to x. All right, that's how inverse works. You just swap the two and throw your inverse something away. Now, the derivative of sine y is let's see, will this work? Derivative of sine y. Okay. So the derivative of sine y will give us cos y dy on the x, and this is equal to 1 because the derivative of x gives us 1. Now, we are finding dy dx, and dy dx is equal to 1 on cos y. We use the formula cos square x plus y, sorry, cos square x plus sine squared x is equal to 1. So in this case, with respect to x, we just change our x to y, and we get this equation. So dy, first of all, let's make the cos y the subject. So cos y is equal to 1 minus sine squared y, of course, with the root. So dy on the x is equal to 1 on the square root of 1 minus sine squared y. This becomes our final answer. Right. So basically, we just found a derivative. We got 1 on cos y. We use this formula. This is the icebreaker. I have no idea what icebreaker means, but it's one. It sounds well, so let me use it. So this is the icebreaker. Once you get this and you make cos y your subject, you get something that looks very nice. Okay, and this becomes your final answer. So this becomes the proof for the derivatives of trig inverse trig functions. So let's take one example. Let's say f f of x is equal to cos inverse of 3x. Okay, let's use this formula for it. So let y be equal to this y prime is basically 1 on 1 minus 3x all squared, and this gives us 1 on 1 minus 3, sorry, 9x squared. So this formula is not size enough. This not, let me check something. Okay, so there's a problem with the, not with the formula per se, but it's just giving us the what we are looking for with respect to x. So let's try and find one that gives us something more general, right? Let's see. Um, okay, yes, this is what I was looking for. So we can see they both give us something like both of the formulas that we have is correct, but one doesn't hold for every case, right? One doesn't hold for every case. Now, let me explain this. Now, in this case that we have, they give us the formula with respect to x when you have just x. But in this case, we don't have just x, so we can't use this formula. So you have to be careful when you are using some trig formulas, right? So with respect to u, you see that we have the same thing, but also the differential of the u. So once we do this, we have to come and find a differential of the inner something. So it's like we are doing composite functions. You find the differential of the outer everything, then you come and multiply by the differential of the inner something, and you get 3. Your final answer becomes 3 on the square root of 1 minus 9x squared. Can we simplify this? I don't think we can. So this becomes the final answer. Cos we were actually doing a cos, so there's a negative here. There's a negative here. There's a negative. So we bring our negative and we are done. Please, are there any questions? Hope the lesson has not been a waste of time. I'll be very sad if you join my class and it's almost a waste of time. Are there any questions, please? Go over the parametric. Do you want me to go over it one more time or it's okay? Hello, Kojo. Hello, Kojo.
You go
Okay, okay,
inverse trig
sure.
again.
Pardon me, please. Inverse trig rather.
Yes, and the parametric too.
Parametric form. Okay. So let me go over the parametric form. Parametric. Just a minute. So we have x and y giving us these two functions, right? X and y is giving us these two functions. Over the interval of t values, then the set of points x, y, ft is defined on I don't know but this is what you should get right. Like once you understand this, it becomes much easier, right? Once you understand this, it becomes very, 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 very sensible. Okay, so let's go over this formula again. So we are finding dy dx, and they are saying dy dx is equal. So this one looks nicer. Dy dx is equal to dy dt, right? Dy. So it's like you are saying that you are finding dy on dx, and let's say dy dx is equal to dy on dx. Now you have to get two things that you can put here that can cancel out, right? And that's your dt and dt. So let's take this question. Mm, okay. So we are finding dy on the x. First of all, how do we differentiate with respect to t? With respect to t, we have the x on the t. Right? With respect to y, we have the y on the t. They are both with respect to t because like we have t. Like if the t were to be x, we'll have the y on the x, but now we don't have x, so we have the y on the t. The same for both sides of the equation, right? So the x on the t, now t is acting like x. The way you differentiate x in a normal equation, that's how t is acting in this case. So you get 1 minus 2t. And with the case of the y also, you get 1 minus 3t squared. Now, how do we combine these two? That's the question. How do we combine these two such that we get the y on the x? Because in this case, you are having the x on the t and the y on the t. When you multiply, you don't get the y on the x. Rather, we divide. So when you divide the y on the t by the x on the t, when you do this division, you basically get the y on the t times the t on the x. So again, you can see that this can cancel out and you get your original dy dx back. So this is basically equal to your dy on the x. If you look closely, you can cancel it out. Now, so we have to first get our dy on the t and our dt on the x. Our dy on the t has been given to us directly in this equation. So we have 1 minus 3t squared. And our dt dx hasn't quite been given to us. We got the x on the t is equal to 1 on t 2t. But we are looking for the t dx. So we reciprocate it and we get the t on the x is equal to 1 on 1 minus 2t. Right? So the t dx now becomes, remember we are multiplying, right? So 1 times the top and the denominator becomes 1 minus 2t, and this dt on the x becomes our final answer. So once you are able to do this part, you are good to go. Okay. Once you do this part, you are good to go. I would have loved us to take a question on higher derivatives, but the solutions are so long and so crazy. So I'll not be taking any question on higher derivatives. I'll be sharing some solutions to us so that we can go through them ourselves. Okay. Please, are there any questions? Okay. Any questions, please? The last example of inverse trig. Okay. Last example of inverse trig. Inverse trig. Inverse trig. Okay. So for the inverse trig, this is the formula we are using. Okay, these ones are strictly formulas, right? This is the formula we are using. Okay, so once you have the derivative of, let's say, sine inverse of u is basically equal to u prime on the square root of 1 minus u squared. Now, in this case, right, we are finding the, in this case, you are finding the derivative of cos inverse of 3x. So the derivative of cos inverse of 3x becomes our u prime in this case. So we are using this formula, not for the sign, we are using the cos formula. The only difference is the negative, right? So we have negative of the derivative of the inner function, which becomes 3. This on 1 minus the square root of the inner function, which is 9x squared. So this is strictly formula work, like it's strictly formula work. So we have to choose this ones. We have to choose it. It has a particular trend, so you can see this one and this one. The only difference is this minus tan and cot, again a minus, and with this ones, let's just really don't come, but you can also choose the formula for it, right? Yes. Okay. So this will be the last thing that we would be doing for today. For the 1 to 6 classes, be at 6:30. Stop recording. How do I stop recording? So for the 1 to 6 class, it would be at 6:30.